Yihong Wu to the CCSP seminar. Yihong received his PhD at Princeton University in electrical engineering. And then he followed it with a postdoc fellowship at the Wharton School at UPenn in statistics. And then he joined the faculty at UIUC, the Department of Electrical and Computer Engineering. And now he is with the Yale University Department of Statistics and Data Science. Yihong's research interests are in the theoretical and algorithmic aspects of high-dimensional statistics, information theory, and optimization. And Yihong's work has been recognized in many ways, and I'll cite only an early recognition and a more recent one. The early one is the 2011 Marconi Society Paul Baran Young Scholar Award, and the recent one is the 2018 Alfred E. Sloan Research Fellowship in Mathematics. Now, Yihong has an enviable habit of breaking new ground in his research, and so we're looking forward today to learning from him about the automatic choice of model complexity that emerges in non-parametric maximum likelihood estimation for mixture models. Yihong, all yours, and thank you.
Thank you very much, Prakash, for the introduction invitation. Yeah, so I will discuss some optimization problem that arises in statistics, in particular about mixture model. And this is very much analogous to computing capacity, where we want to maximize the concave function over the space of measures. And I will discuss some classical results and the more recent results obtained in a joint work with Yuri Polyansky, who was at MIT and recently has moved back to Moscow Institute of Physics and Technology. There's nobody was shocked. So it's April Fool's Day, right? So this is the only joke I will make. So he's still at MIT.
We took it seriously.
So yeah, so I think, I mean, I was told that for this seminar, I should go a bit slow and give most of the details, and I'll do exactly that. So I will not present all the results, and instead I will focus all the attention on very simple model of mixture model, just the Gaussian mixture model, and you can think about this as the Gaussian convolution of a distribution with Gaussian density, or think about the output distribution of a additive Gaussian channel, if you will. So let me start with the setup of the problem. I have, wrote this down beforehand just to save some time, and then when I proceed to the explanation of the technical content, I will write in real time. So in Gaussian mixture model, your data, let's say a sample of size n, are drawn independently from a Gaussian mixture. Here I write it as a convolution between a standard Gaussian density. This is just a density of normal 0, 1, denoted by phi, convolved with the distribution pi. And this pi is commonly called mixing distribution. And the mixture is just the convolution of the mixing distribution with normal density. Okay, so you have n data points of this form, and the goal is to learn something about the mixing distribution pi, right? So specific goal today, I was just going to discuss one procedure, which is just the maximum likelihood. So maximum likelihood here is the estimator of pi by means of maximizing the likelihood or the sum of the log likelihood. And the maximization is carried over all probability measures on the real line. Okay, so this is the reason such a maximum likelihood estimator is called MP maximum likelihood, where MP stands for nonparametric. And this was introduced by Kiefer and Wolfowitz in the 50s, and it has become a staple not only in learning mixture models, but also in empirical Bayes. So I won't have time to discuss this. I'll mention it briefly after this page. But the goal is very simple. There's this objective function, which is the likelihood, and this is the function of the distribution pi. and I want to maximize it over all probability measures. This sounds like a difficult thing to do, and also sounds like a very much like maximizing capacity, if you will. But then I will actually show you it's exactly analogous to solving the rate distortion problem for appropriate in appropriate sense. Okay, so this work with Yuri Polyansky, our goal is to understand the typical structure of this solution. So I will explain in the first part of the talk classical theory on the structure of this solution, in the sense of existence and uniqueness and discreteness. And this was proved in a worst case, for worst case realization of the sample. So the new results obtained last year in this paper give you some insight about the typical behavior of the solution. And in particular, those new results will be useful in deducing its statistical property, as well as understanding the claimed self-regularization phenomena. And those are not explained by classical theory. So then I will also discuss some connections to information theory, especially the connection to rate distortion function, and also to the capacity problem. And I'll end with some open problem. Actually, the results we obtained in this work, I think it's just a very modest start of understanding such optimization problem. Okay, so feel free to interact at any time. So before I go into the technical part, let me make a few remarks about, I haven't explained why do I call this convolution mixture, Gaussian mixture, and then I'll explain now. So if I write the mixture density, which is the convolution of pi and phi, as a function which is f of pi, this is, if you expand the convolution, it's phi x minus theta integrated average theta over the pi. And I can also write it as expectations, right? So it doesn't matter. So the reason this is naturally viewed as a mixture can be understood, for instance, in the important special case of a finite mixture, where pi is just a discrete distribution with k locations and k weights. Yes. So here, the W's are the weights, the thetas are the locations, which we call the atoms. So this is a k atomic distribution. And the convolution of a k atomic distribution with the Gaussian density is just a superposition of k shifted Gaussians. Yes. So in this special case, the density is just the convex combination of a k different normal density with centered at mu1, mu2, and mu_k, and weighted by w1 and wk, right? So this is the reason this convolution exactly is what mixture is. And the reason it's in this, I mean, not all mixture models are convolutions. Location models, meaning models indexed by the mean parameter, are convolutions. So this is the simplest possible Gaussian mixture model that you can think about. You have k components, you have k mean parameter and k weights to learn, right? So essentially the number of parameters is 2k minus 1. And the difficulty of this problem is the likelihood is non-convex in the centers. And this is a fundamental difficulty, which essentially is why the EM algorithm was invented. So this maximization problem, if you view it as a maximization over the weights and the centers, the weight part is fine, it's perfectly concave. So it's easy. So the center part is non-concave, therefore there's no provable algorithm to optimize it. And this is the starting point of the EM algorithm, which iterates between optimizing a concave minorand of the likelihood. So, and then people know that because of the intrinsic non-concavity of the objective function, even if you have infinite amount of data, EM algorithm can still get stuck in certain spurious local maximizers. So essentially, you can think about non-parametric maximum likelihood as a way to circumvent the non-convexity in this original parameter by means of over-parameterization. Right? Even if I know, let's say, the task is to fit a 4-component mixture of Gaussians, I will, instead of maximizing over the location parameters which are non-convex, I will over-parameterize it by infinite mixture of Gaussian, by just treating it as pi convolved with phi and forgetting that pi is actually 4 atomic, and just maximizing pi over all measures and hope for the best. What's the point? The point is that the problem becomes convexified, right? Essentially, I'm solving a convex relaxation of the problem. And this over-parameterization, of course, runs the danger of overfitting, right? Because I have decided to parameterize my model using a measure, right? So maybe the fitted model is too complex, right? So this is the problem that was the starting point of this research. Is, what is the typical behavior of this solution? Does it genuinely give you a very complex distribution, or it actually fits something simple automatically? So let's say if the true model only has 2 components, right? What's the typical size fitted by the model? Is it 2 or is it super large? So on and so forth. So this is the question that this work aims to address. And these are not addressed by classical results. So, and last 2 things I want to say, just for context, is that the non-parametric maximum likelihood is the method of choice for a very important method called empirical Bayes. So empirical Bayes is a method that goes beyond worst case analysis in statistical, let's say, denoising. So it pretends the data are generated from a prior. Instead of using a pre-agreed upon prior, you learn a prior from the data, then execute the learned Bayes strategy. And the NPMLE has emerged as the method of choice for learning such a prior, for the very simple reason for its simplicity, although it looks very complicated, and also for the lack of tuning parameters. There's nothing to penalize. There's no tuning parameter. You just choose it and then run. So, and the reason this optimization problem is infinite dimensional, right? I want to maximize over a space of distributions. In fact, has many different fast algorithms. Many of them are of iterative nature for computation in 1 dimensions. So this is the limitation, and 1 dimension is what I will focus on today. And the reason is we know nothing about it in 2 dimensions. Even the classical theory is a vacuum. Okay, so let me start with the classical results, and I will describe it, and I will start to write the proof down. Okay, so the classical results explains the structure of the solution in the worst case sense. So this was started by Simar in the 70s, who studied the Poisson mixture instead of a Gaussian mixture, and then followed by Joel in the 80s, who studied actually the mixture of exponential distributions, and then followed by Lindsay in a sequence of paper that culminated in his 95 monograph that essentially gave a definitive answer about this mixture nonparametric maximum likelihood in 1 dimensions for all exponential families. And I will only discuss Gaussians today. Essentially, many of the ideas are common and was already presented in early work. So let me write down the objective function of the maximum likelihood, which is just the sum of all the likelihood all the likelihood values. Right? So f of pi is, remember, is the convolution, and evaluated at the I sample, and I aggregated, and this is the objective function, and this is a concave function of pi, just because of log. And the nonparametric MLE estimator is the maximizer of this thing over all space of measures. So I write this as a space of all measures on R. And I wrote equal to because in principle I should have written like this, right? Because who knows how many maximizers there are. And the theorem, which was due to Lindsay, says the following: for any realization of the sample, so this is purely deterministic results. This maximizer exists and is unique. And in addition, it is a discrete distribution with at most n atoms. N is the sample size. So I will give you the entire proof of this, and then jumping off this proof present new results. Okay, so let me make some comments about this thing. So so this is, as I said, a worst case guarantee that works for any realizations. Actually, it's not possible to improve as stated. So think about it. What does it mean? It says if you have 1,000 observations and you chose to fit a mixture of Gaussian model, the theorem says you will not fit more than 1,000 components. This is useful, but not that useful, because if you want to answer the question, does it overfit? And if you have 1,000 data points, you fit 1,000 components, it sounds very much like overfitting. Ideally, you want to fit a small model, maybe with 3 or 4 components. But in the worst case, this is not possible. So let me show you some pictures, some simulations. So this is what happens in one configuration of the data where the data is very well spread out. So here there are 11 data points separated by 3, I think, 3 times the standard deviation. And then I ask this nonparametric likelihood to search for maximizer over all measures. It actually returns a distribution with 11 atoms. And if you think about it, this is in a way making sense, because suppose your data is so separated and I insist to fit a mixture of Gaussian model, maybe the best explanation to such a data is just each data point is its own cluster, and the weights is equally spread out. And this is indeed what the density, fitted density looks like. There's a lot of maximums corresponds basically to the raw data points. And you can imagine this happens, if data is so spread out, it will genuinely fit a gigantic model. But of course, the catch is that this is not a typical situation. Right? If your data are drawn independently from a true mixture of Gaussian model, they will tend to cluster like this. Like this, sorry. Right. So in this case, again, there's 11 data points drawn from a mixture of 2 Gaussians. So they tend to cluster, or they don't tend to be so spread out. And once this happened, if you feed into the algorithm, it will return to you a small model. And this blue one is the fitted density, which kind of explains these 2 clusters. So this is what happened in practice, is that the theory, as stated in the worst case, is tight. But in practice, it's observed that the solution is typically simple, has much fewer than what the worst case theory promises. So this is the reason that there's a need to have a theory that explains this typical behavior. And that is what is accomplished in this paper. At least I hope the motivation and the statement of the classical results is clear. Feel free to interrupt with any questions.
Oh, very clear. Thank you.
Thank you very much. So let me take a slight detour to explain the needed technology for proving these classical results. So this is of general interest. So this notion called Haar system or Chebyshev system shows up in many different places approximation interpolation. So let me define it, and I'll explain the role it plays in this proof. Okay. So I have n functions, f1 and fn. These are real valued function on the real line. And we say that they form a hard system if the following condition is true. Any non-trivial linear combinations of these functions has at most n-1 real roots. So this is the defining property of a hard system. So in other words, you can think about this as a basis. These n are linear independent functions. Think about them as monomials, right? So this says something about how many roots a polynomial in this generalized sense can have. Okay, so let me write it, the mathematical definitions. So in other words, for any weights W1 to Wn that is not all zero, the function Wi of fi of theta has at most n-1 roots in R. Okay. Yeah, is this clear as list definitions? Okay, yes. So let me rephrase it in two different ways, and both of them will be useful for us. So equivalently, this is stating the following: for every distinct points theta1 to theta n in R, and for every, there is no for every, then the matrix f of I theta j, and this is matrix, which is n by n matrix, is invertible. This is literally the rephrasing of this statement, if you think about it, right? If there are n roots, then plug in these thetas, define this matrix, will make it have zero determinant, right? And then vice versa. So these algebraic styles of definitions can also be phrased in this more linear algebraic way. Okay.
Yihong,
yeah, please.
Actually, the algebraic definition has problems because notion of multiplicity is hard to define for general functions. Right? So.
Okay, you're right. Yeah. So here, let me just say that I'm counting. I'm just counting without multiplicities.
Oh, but then you wouldn't be able to cover polynomials in that case. I just wanted to say that the matrix definition is much more clear. That's all.
Oh, okay.
Yeah.
All right. Okay, so let me start with another way to say it. So this is more in terms of interpolations. For every distinct nodes and for every values, their linear system, which is the sum of wi's fi of theta j, theta j's, j's, I think. No, i's, is equal to yj 1 to n and j from 1 to n has a unique solution in W. This is saying the same thing. So essentially, you can think about, I want to interpolate n pairs of points using linear combinations of such a function. And then there is a unique choice of coefficients. And indeed, you can interpolate n points. Okay. Right, so let me give you some examples and non-examples. So the first example is monomials. is a hard system. And the reason is, well, we know that degree n polynomials has at most n roots. Or equivalently, this matrix F is a Van der Monde. Right. So let me go back to what Venkat said. I think here, if I don't care about multiplicity, the result as stated is true. Do you agree? I mean, multiple roots is just, I view it as one root. So the result as stated is fine. In fact, I even kill the complex roots. I just said it's a hard system. I don't think there's anything wrong with it, right? You're muted.
Yeah, I mean, it's not an important point, right? It's just, if you want to define a hard system, you probably want to allow for the notion of multiple roots if you want to include polynomials.
Yeah, for this talk, I elect for this definition. It works for my purpose, I think.
Sure, okay, that's fine.
Yeah, okay. So the second thing is, if I kill the constants, theta square, theta n is not a hard system. And this is clear, right? Because linear combination, the degree is dictated by the last guy. So the lesson I think here is that subsystem of a hard system need not be hard itself. Okay. The third example is exponential polynomials. So let me start with exponentials. x1 theta, x2 theta, xn theta is a hard system. Oops. And these exponents are distinct. And the fourth example is I can also introduce some polynomials. So e of x1x, e of xnx, I add theta times exponential. And this becomes a hard system of size 2n. And I'll prove all of these. I mean, the 3 and 4. And the fifth is shifted Gaussians. Again, these centers are distinct, is a hard system. Okay. And we'll need all of these for the proof I mentioned, which was known before. Okay, so if there's no question or comments, I'll proceed with the explanation. So the explanation is this. So our proof of 3 and 4, they all relies on the following generic fact. So let's say this is a lemma, and you can find this lemma in the it's an exercise from Polias-Siegel, volume 2. So if you have n polynomials, and these are polynomials, regular polynomials of degree, let's say d minus 1. And then if you the summation of pi theta times exponential xi theta has at most nd minus 1 roots in R. Okay, so d equal to 1 is the previous results labeled as 3. D equal to 2 is this 4. And the proof is very simple. So it's based on the interlacing property of the roots of the function and its derivatives. So the fact is that if you have an analytic function, very smooth function, that is like this. We use a different color, right? And here are these roots, and here are the roots of its derivatives, which are exhibited as local min and local max, right? So if you have a very nice function, then the roots of f and f prime are interlaced. Okay, so let's prove this by induction on n. So the base case, which is n equal to 1, is very clear. So number of roots of p1 theta ex1 theta is equal to number of roots without the exponential part, and this is at most d minus 1. So this is the base case. Give me 1 second. Sorry. And the induction happens in the following way. Suppose the function, let's call it f of theta, f has k roots, then this is equivalent to stating that let me remove the last exponent by dividing it on both sides. So this means the function pi of theta e times xi minus xn theta 1 to n minus 1 plus pn theta k roots. Right. If I take one derivative, I get pi prime theta plus xi minus xn pi theta exponential plus pn prime has k minus n roots. And I've keep doing it until I eliminate the last term. And the whole point is that this quantity remains a degree d minus 1 polynomial, right? If I do it for a few times, I will get some other polynomial of pi prime pi tilde times exponential xi xn minus 1 theta plus nothing. And there's n minus 1 term has k minus d roots. And by induction hypothesis, this is bigger than n minus 1 times d minus 1. So that's the proof, right? Okay. All right. So let me prove the last thing that will be needed for the this mixture thing. This is about shifted Gaussians. So here it's more convenient to take this determinant linear algebraic rephrasing of this thing. So what I want to show is that this system theta minus x1 is a hard system. So equivalently, what I want to show is this matrix F, which is xi minus theta j is m by n matrix, is invertible. Okay, so I will show that this is just a consequence of the previous hard system property of the exponential function. And this, if you expand the quadratics inside the exponentials of the Gaussians, you'll get this is literally equal to, I think, some constant times e to the minus xi squared over 2, e to the minus theta j over 2, times the cross term, which is theta I xj, right? So in other words, what it means is that f in terms of a matrix is equal to the product of a diagonal, d1, times some matrix f tilde times d2, where this is diagonal with e to the minus xi over 2. And this is diagonal with the theta part. Yeah. And this is that. Right. So the determinant of f is equal to the determinant of the product of 3. And this is not 0. This is not 0. This again is not 0. Why? Because we have shown this is a hard system. Okay. So that's the idea. I think there are many different ways to prove this. You can also take derivatives of the Gaussians and do what we just did before. This is just another way to see it. Okay. So let me mention an application of this result. Oh, I have some problems with it. And this application will be applied subsequently in the proof of the classical theorem. So the application is the following statement: any n-component Gaussian mixture, and I will just call it NGM, has at most n modes. Modes understood as a local max. So what I mean is that if you have a function of this form, just a superposition of n different Gaussians, how many different maximas can you create? Well, if you have a budget of n Gaussians, by shifting them around and appropriately weight them, you can create at most n local max. And this is sort of, this picture is the best that you can do. Make them very far apart. And this is also tight. So the proof is simple. So what I want to understand is if you have f, suppose f has m plus 1 maximas, then in between maximas, you are going to have some minimums, right? And this is true for any nice functions. And it's true in life in general. So between these ups, you have some downs. And then in total, you're going to have f prime. This implies f prime has 2m plus 1 roots. And we'll show that this is not possible by evaluating the derivative. The derivative, if you take derivative of each Gaussian and then take the linear combination, you're just going to get the following: wi of xi minus theta of the Gaussian xi minus theta. And then I can write it in this way. I have n terms, wi phi of xi xi minus theta. This is not possible to have 2m plus 1 roots because of the fact number 4, which says e to the x1 theta xn theta theta x1 theta theta xn theta is a hard system. Okay, so this is the classical results. So let me make one remark on this page. Then I'll go back to proving the theorem previously announced. All right. I want to move it up a little bit, just need a little bit more space. So the remark I want to make is that what happens in d dimensions? If I give you a budget of n Gaussians in 2 dimensions, how many maximas, let's say local maximas, can you create? Can you do more than n? So this actually took a long time to be resolved. The answer is yes, if you care about local maximas. So there is a famous construction that looks like this. So you put a triangle and you put 3 Gaussians centered at the triangle. Of course, you're going to have 3 maximums at the vertex of the triangle, but because of these Gaussian adds up inside the triangle, there's an added local maxima in the center. So in this case, this is 2 dimensions, 3 component, but actually you created 4 modes. So then there's a question, if you have many Gaussians in 2 dimensions, how many can you create? And the answer is, I mean, we know it to some extent. So there's some precise conjectures, but people know the following number of local max, which is what I call modes, is upper bounded by some constant factor times n to the dimension, and this is tight. So in other words, there's a systematic way to create examples of this form, but at a much bigger scale in any dimension. And it creates many more maximas than n.
So Yihong, I have a question.
Yes.
So there's this theory of so-called real stable functions and so on that many people are looking at nowadays. It's supposed to be the multidimensional generalization of this whole real rooted polynomial story.
Mm-hmm.
I mean, what you showed for the Haar system basically based on interlacing and so on, right? So
Yeah.
my question is whether there's any attempt to use that theory in the multidimensional case.
So these results, one side is a construction. So this one, I don't remember how did they do it in the more systematic way than this triangle. But for the upper bounding number of roots of the gradient, the keywords they use is this thing called phenomials, which is extension of polynomials where you introduce exponentials and so on and so forth. So there's a theory which is very much rooted in real algebraic geometry, which I have no understanding whatsoever, tells you about roots of these vector valued functions.
Yeah, so basically the same thing that I'm talking about.
So they called some results from a book actually titled just called Phenomials.
Oh, okay.
And then
no, but nowadays there's something called people study something called real stable functions, which
yes,
it's also part of real algebraic geometry. Yeah. In any case.
Yeah, I heard about these real rooted polynomials and the application in TCS more recently. Yes, but here this is outside the realm of polynomials. So I actually don't know. And the reason this was essentially there's a big vacuum of any results, classical or these typical results, even in 2 dimensions. So, and let me just make another remark. number of global maximums, which is actually what is needed for the theory. How many there are in total, and this is completely open. So I don't think there is a construction that actually constructed more than n global maximums. So I think maybe the running conjecture is that with n Gaussians in arbitrary dimension, you cannot create this oscillation more than n times if you're looking at the global max. Okay, and I'll come back to that later. So let me explain. Yeah, so I think this is already, yeah. So this is the proof of theorem 1. And yeah, so let me explain how the stuff I just presented can be used. So recall the objective function is the total log likelihood. And also remember f of pi is the convolution, which I can also write in its expectation form, right? So this is just expectation of a shifted Gaussian, which is called fi. Fi is just the Gaussian shifted by amount of xi. Remember, xi are these data points. Okay, so this proof proceeds in a few steps. So let's be more careful about it. We cannot directly apply the results I just announced to prove this thing. So let's do it first. Switch the optimization to a slightly different domain. So let's define a convex set, which are just the values of these expectations. Right. So have n different functions, which are shifted Gaussians. And for each, I take expectation over a common distribution called pi. And I go over all distributions. For each distribution, it gives me an n tuple. And these moves around and trace out the convex region in Rn. And this is nothing more than just by continuity of these functions, the closed convex hull of this curve. So it's just the evaluation at each theta and then take the convex hull. Whatever it looks like. I don't know how to describe it, but this is some compact and convex set in Rn. Then it's clear to see that the optimization for the regional objective function is literally equal to optimization over this just rewritten form over f when f ranges over this domain. Right, this is just definitions, nothing else. But now the benefits of this restatement is that the optimization over the right-hand side has a unique maximizer. And the existence is just because the function is log function is continuous here over the domain, and the domain is compact, right? So the maximum is hit at some point. And because the log function is strictly concave, so you cannot have two different maximizers. And that's it. And this magic maximizer, let's call it f star, right? Once you give me n data points, this f star is frozen. So let's freeze it. It's called f star. And notice that this uniqueness is in the f domain is just because of the strict concavity of the log function. In contrast, the regional function in terms of pi is actually not strictly concave. It is concave, no problem, but not strict. Therefore, we cannot conclude the uniqueness of the maximizer in pi yet, but we will in a few steps. Any questions about this at this point? No? Okay, so we will use this f star vector, right? So this is some vector that is unique, so let's use it. So what remains is to show that this actually admits a unique representation. Okay. But before that, let me just make a remark. By using Carathéodory theorem and this strengthening, which was used all the time in information theory for alphabet reduction, what you can show is that as far as the maximum is concerned, you can always achieve it with a distribution with n points. And this is just a simple application of Frankel-Eggleston Carathéodory, because it only touches upon n expected values, right? So whatever pi you gave me, I can recreate the same pi, same expectations using a distribution with no more than n atoms. Right? But this tells you only that there exist a n atomic maximizers. Right? Suppose someone proved to you it's unique, then it's done. Then the n atomicity is for free. But this actually goes hand in hand, because to prove uniqueness, you need these structures. And this was proved next in a different route. Okay, so just a clarification in case you were thinking about alphabet reduction type of argument. So in this magic F star, what we need to show is that you can only find a unique pi star whose expectations give rise to this F star. Right? So this is the goal. And this F star is just the maximizer. And so this will prove everything that we need. And for this, we have to go back to the optimality condition of the regional optimization problem, which is I have this objective function, and pi star is, well, the global maximizer, right? And then it has to satisfy optimality condition, let's say the first order optimality condition. So if pi star is the global max of this objective, then I can perturb it, and it will not improve my objective, right? The perturbation I'm going to consider is of a very specific form. So I'm going to add one more component by including one more delta function into the solution and appropriately rescale the previous one, right? To take convex combination with a new atom. And this will only make my objective worse. And this is just the necessary condition of optimality. So this must hold for every possible theta and for every possible weights, right? This modification will lead to a worse objective function. Therefore, the derivative at epsilon equals 0 of this thing must be non-positive. So this is the usual thing. And let me just comment that this is also sufficient. It's also sufficient for optimality because of the concavity of the objective function. This you can show just by hand. Okay, so let me compute the derivative, which is very simple. So this is just the following sum of log 1 minus epsilon times what? Times fi star, which are frozen, plus theta times phi of xi minus theta. So you take derivative of logs, you're going to get something on a denominator. So this derivative is just a summation when if you evaluate it at theta equal to 0, fi star phi of theta minus xi minus 1. Okay, so that's what this is. So you can also write it as d of theta minus n, where d of theta is just phi of theta minus xi, fi of star. Right. So the conclusion is that we have this function, which is the directional derivative of the solution along a perturbation of a singleton, right? Which is f of I star d of theta minus xi. Satisfy the following property. Number 1, d of theta is less than n for all theta in R. And this is from the first order optimality condition. Number 2, and this is the most smart part of this argument, is that if you average theta according to pi star itself, if you average theta according to pi star itself, you're going to get exactly n. And this is just because the average of this is equal to the denominator by definition. right? So, and this creates a very clear picture of what the behavior of this D function. So this D function must look like the following. Theta, and this is n, and this D function hits the ceiling at a few places, and these maximas are exactly the support of pi star. And this is the only possibility, right? If you have a function which is bounded globally by some number, and if you average under a certain distribution, you exactly hit this number, and this distribution must be supported on the global maxima, right? So this means the support of pi star is a subset of the global maxima of D function, which is further included in the local maxima, which is also included in the critical points. Okay, and now this is the end of the proof. Why? Because d theta is just a convex combination, just a linear combination of n Gaussians. And then by using this step, and d theta is proportional to the n Gaussian mixture, hence has at most n local max. Right. So this proved that. So let's denote them. Denote them by x1 star to xm star. That means less than n. So I know that whatever the solution is must be supported on these at most m points. And these m points is also, frozen. There's nothing else to choose because f of I of star, these coefficients are frozen from step 1. So this is some fixed function that exhibits these local maximums. And these local maximums, on top of that, well, you can have different weights, right? So the last step, which concludes the proof, is to show the uniqueness of the weights. Step 3 is the uniqueness of weights. Let's say W1 star, Wm star, that satisfy this representation such that if you take the linear combination of Wi star, phi of, I think I should have used a different notation. So this should be theta. It's better to denote it by theta. Theta I star minus xj is equal to f of j of star. J is equal to 1 to n. And I is from 1 to m, and m is less than n. And this has unique solution because, well, the shifted Gaussian forms a hard system. By previous number 5. Yeah, so this completes the proof. And you see that this uniqueness actually crucially relies on these quantitative estimates here, right? So suppose I can only conclude it here has, I don't know, like in 2 dimensions n squared points, then this won't work. Right? Because I only have n equations, because this is dictated by sample size. If the support point exceeds n, then hard system argument is useless, right? It won't allow me to conclude the uniqueness of the solution. So this is the reason I said this thing you can extract automatically from a Kerr theory style of argument. Kind of goes hand in hand with the uniqueness argument. Okay. So that's the, yeah, please.
No, yeah, it looks like you proved the uniqueness only when you have the maximum number of extrema, is that right? Because if you go to the next page, you seem to be appealing to the size of this matrix being big enough somehow.
So here, n is less than m, right? So I have m variables, n equations. So this, because this full system is hard, so you cannot, I already know there exists a solution. So I cannot find two solutions. Otherwise, this matrix is rank deficient.
Yeah, but the number of theta I star you need is should be big enough in order to conclude that the matrix is non-singular, though, isn't it?
No, here is not that, right? So here, what do I do have is I have n equations. So this is the W, this is the F, and I have n variables. M is less than n, so it's possible to be a square one. But your concern is that maybe it's not square, then it's a tall matrix. Then of course you cannot create multiple solutions of this linear system because it's tall.
Okay.
Yeah. I mean, if you want, you can augment it to make it square, right? So this proves, I think, unconditionally the solution is unique.
Okay.
Yeah. All right. So so of course the new results will also take ingredients from here. I think what is learned here is that to counting certain local maximum of some function of this form, in particular, it's a Gaussian convolution form, is going to be useful to us. And here we want to go beyond what this type of argument promises.
Yihong, I'm getting some I'm getting a peculiar picture here, right? I mean, you're doing an optimization over some convex set.
Yes.
But you seem to be finding something almost like a polyhedral decomposition of that set. In a sense,
so you mean
being defined in terms of the number of extrema of, I mean, something which is extraneous to the fact that, I mean, extraneous to just the convex structure. There's some notion of local maxima for the points in the boundary of this convex set. And somehow single data points seem to pick out only the vertices and double data points pick out the lines and some funny system like that, right?
I didn't fully understood.
No, so I'm thinking of parametrizing the space of all these convex Gaussian mixtures by this distribution you call pi, right? Which is the mixing distribution.
Yeah. Yes.
So,
just arbitrary distribution of R.
There is some extraneous notion, which is that if I take a particular mixture, then I have a notion of how many maxima it ends up displaying. And I seem to be finding that if I do an optimization problem where I have just a single data point defining the direction in which I want to optimize, then I'm finding a certain subset of boundary points, which sort of are like vertices in some polyhedral decomposition. If I have two data points, then I seem to be finding that things lie on things I would call lines and so on and so forth. So somehow there's a structure to the space of all possible mixtures, which is almost polyhedral, even though it's somehow like a round object in some funny sense.
So so let me clarify two things. So first, the maximas of this derivative is not directly related here, right? Because that's just part of the optimality condition of the optimizer. And the second thing I want to say is that if you restrict yourself pi to, let's say, distributions with at most k atoms, and this is a non-convex set, so somehow this solution says it's as if if you have n data point, you are solving this non-convex thing exactly.
Yeah, but
by solving this, I'm not sure if I understand your point, but this is.
I'm not saying anything about the derivative. I'm just saying, I'm sort of just trying to rephrase what you seem to have proved in geometry, in a geometric notion. So I have the space of all possible pi's in some sense, right? And that's a convex set. But individual choice of pi, I have a notion of some number I can associate to it, which is the number of maxima of the corresponding Gaussian distribution, which is something which is extraneous to just the convexity, because it's it just depends on the fact that I'm looking at a specific kind of distribution associated to pi, namely the Gaussian mixture associated to pi.
Just convolve with pi. Okay.
Yeah, and that has a certain number of maxima. Right?
But that doesn't play directly a role yet.
No, but that's showing up in the solution, right? When you try to optimize, you end up finding solutions that end up having only n centers.
Actually, that's not true. So this function is not pi convolve with normal. So that's the point.
Oh, I see. Okay.
So this function is
okay. No, I understand my confusion. All right, thank you. Yeah. Okay.
So this is not the fitted density.
Okay.
Yeah.
Thank you.
So this is some strange object which is defined by the global maximum itself. So it's a tail biting condition, if you will. So it says the optimizer must fulfill self-consistency type of thing. If you compute this thing, which is the reweighted Gaussian by this fitted likelihood by itself, then the maximas must be consistent with its own support.
So you're saying that the underlying pi might actually have continuous support?
This argument tells you that it cannot be.
But it doesn't. It can have a number of points which is different from the number that you see of the peaks. Is it?
It's contained in these peaks.
Okay.
Yeah. I mean, maybe some of these weights are zero.
My picture is once again valid, right? I mean, somehow. So this, I can just think about the polyhedron in terms of the number of centers. I don't have to think of it in terms of these peaks. You still have this phenomenon somehow that if you sort of test, if you do an optimization in a direction defined by k samples, then you end up getting an extremum which ends up having at most k centers, so to speak. And that to me is a funny kind of polyhedral structure to this.
So maybe let me draw one more picture. So this is d of theta. This is from the optimality condition. It's not obvious what it is, what it means. So let me plot what the fitted density looks like. Maybe it will look like this.
Yeah.
Yeah. They're on the surface. They are distinct.
No, but the fitted density also has at most k centers, right? It's a convolution with a
Sure.
Mm-hmm. Yeah, so that's what I mean. So I want to keep track of that count, and that sort of decomposes the space of all possible pi's in a sequence of levels, right? Which are like
okay.
Yeah. And so I mean that seems to me somewhat something polyhedral, some kind of infinite dimensional polyhedron, which you normally don't expect such a structure for optimization over round objects. So I'm just wondering whether that means anything or
not. I'm not sure at this point. Sorry.
Okay, maybe I'll take it offline. Thank you.
Yeah. Okay, so all right. So let me continue with the new results. So I think this is I forgot. So let me just say the new results. So new results is a theorem that has two parts. So the first part is deterministic. It says for every x1 and xn, before I can only bound this solution using sample size. Here, let me bound something which is sample size independent, which is just a range of the data. So it's bounded by some c times x max minus x min squared. So this x max is just the maximum of xi, and this is just the minimum of xi. And this c is a universal constant. So this is the proof, this is a result which is deterministic. And as a corollary, let me just state its statistical version, where actually the xi's are drawn from some distribution. Statistical result. Let me continue the previous setting where you have a sample of NID observations drawn from some ground truth convolved with phi. So this pi is the true pi, where pi has some nice tails. Let's say it's one sub-Gaussian. The constant is not important. And then what this result says is that with high probability, with probability 1 minus little of 1, n tending to infinity, support of this solution is at most log n. Right. And this is just a one-line proof from the deterministic guarantee. Let's take union bound, right? By union bound, each of the xi's, because they with probability polynomial is small, is between plus minus root log n. So square it, you get log n. Yeah.
Yihong, what is the significance behind the square in part A?
I wouldn't say it's significant. It's a result that is just tied, so you cannot improve it.
I see. Okay.
Yeah.
All right. Thanks.
So yeah, I'll explain why.
Okay.
So let me make just a few remarks. The first remark is that it's possible to extend to other distributions, not just mixture of Gaussians, but it's limited to tails, which is strictly faster than exponential. The equal to, like Gaussian, is fine. So the proof is more involved. But by extension, I meant these log n results continue to hold with high probability. So you might think this is, well, it depends on the Gaussian tail. If I make the tail lighter or heavier, log n would become root log n or log n square. But in fact, it's universally true. I mean, subject to this quantification. And to go beyond to other distributions, even to simpler exponential mixture, which was literally the second paper on this topic by Joel, was out of reach at this point, actually. So there's a lot of limitations to these results. I'll explain. And then finally, let me just say that log n is optimal. So you can see it in two steps. So in other words, this is the right model size. So log n it suffices to fit a log n sized mixture model by approximation, because any such mixtures can be approximated by a mixture of Gaussian with log n components up to total variation that is 1 over n to the 10th, let's say. So within this total variation approximation accuracy, I can simulate your sample with the new distribution, couple them with high probability, right? So within this total variation approximation error, there is no ground truth. They are all ground truths. So there is no statistical reason to fit a model bigger than log n. Otherwise, so, and somehow this infinitely parameterized, over-parameterized optimization will not fit more than log n. And also log n is necessary. To reach known statistical accuracy. So if you fit less than little of log n, just the bias will overwhelm the known statistical accuracy for this estimator. So this can be seen, for instance, using a result of Sergio and myself from 2010 that shows if you want to approximate normal 0,2 using mixtures of normal 0,1 and using k of them, the best approximation error is exponential in k. Right? So if k is less than log n, your approximation error is bigger than any polynomial in N, and this violates existing results. So this also shows you this log N essentially is the effective dimension of the problem. And the reason we call these results self-regularization is that this optimization problem, which actually didn't enforce any constraint, any penalty that encouraged you to search for a small model, automatically find the right model size. So this was a bit surprising to us. And this similar results to this exists for other non-parametric maximum likelihood in shape constraint problems. There's a famous estimator called Grenander estimator for monotone density, which exhibits a similar behavior, but the proof of those results are more aligned with empirical process theory because you can describe exactly what this estimator is using empirical processes. Whereas here, the optimality condition is more involved. So it's not that obvious. So let me conclude this by giving you the proof of these results. The only thing I need to show is this. Okay, so the proof of so remember that our starting point, recall that we know how many atoms there is in the solution of NPMLE is upper bounded by number of global local maximums. And then let's just count critical points of d theta, where d theta is of this form, is just linear combination of shifted Gaussians. And these coefficients are positive. And this is important. And this is crucial for the argument here. Before, the n Gaussians superimposed on top of each other can create m modes at most, even if the coefficients are negative, still it's fine. The result is true. Here it's not. This is crucial. So this is proportional to up to a constant scaling to some wi's. I mean, you need to renormalize these coefficients of this form, which in turn is a Gaussian convolution of phi as some measure. Let's call it mu. Where mu is a reweighted empirical distribution. I have no idea what these weights are, right? Because they depend on the optimizer itself, right? It has this tail biting flavor. So it's hard to describe, but it's some weights. Is supported on the data. This I do know. So it's some reweighted distribution supported on the data points, convolve with my distribution. And this pi is not, this mu is not pi. I think this is related to the previous discussion with Venkat. So this mu is some strange stuff. And the point is that this is included in the interval, in the compact interval between the mean and the max. And this is all we need to show. So it suffices to prove the following lemma. And this is will be the only thing we need to prove the main results, which is let mu be an arbitrary probability measure on the interval plus minus a. And then the convolution with mu and standard normal has at most a square number of critical points. And this is the main results. And furthermore, this a square is tight. So let me comment on the lineage of this result. It was proved independently by Alex Disto, Yagli, Poor, and Shamai, 2020, for an unrelated information theoretic problem. which is exactly the amplitude constraint Gaussian channel capacity problem. So if you remember, there's a classical result of Smith that proved the capacity achieving input distribution is discrete. So this paper of Distel et al. Gave you bounds of how many points there is in this discrete input distribution. So they use the same technology. And this tightness is also proved also by Kashyap and Krishnapur, also last year. So this entails a constructive example, right? I need to exhibit some measure which actually has a square local maximums. And this is not that hard. In the paper, we also gave a construction using just a sinusoid construction with pi with just shifted cosines. So it's easy to create A modes, if you remember the example we did a few times, which is these separated Gaussians, right? So this separation, let's say it's 10. So you can create A modes easily. To create A square modes, it's more complicated. And turns out A square modes is the most you can get. So let's prove this result, and then I think that will be N. Any questions before I do this? Right.
No,
The proof, yeah, please.
No, I said it's fine.
Okay.
Yeah.
So this is the last topic, the proof of this lemma. So we need some tools to count critical points, or in other words, to count zeros of a function. And complex analysis offers many different tools for this purpose. So the one that we're going to use is Jensen's formula. Jensen's formula says, if you have a nice function g and some number r, some radius r, and suppose I want to understand the root behavior of g inside a disk of radius r. So let a1, a2, be and the roots, complex roots of g inside disk of radius r. Then there is identity that relates the roots to the integral of g on the circle of radius r. So if you sum all the roots of log of r over the modulus of k of the roots is equal to the average from 0 to 2 pi, g evaluated on the circle divided by size at the center, and that's it. So this is elementary results from complex analysis, and the consequence offers us some way to count number of roots within a given radius. So suppose you have some handle on the size, the maximum size of this g function on the circle, and then the right-hand side is bounded by log of the maximum on the circle and the center, right? And suppose there's some small radius r, then I can bound the left-hand side from below by only taking into account of roots that is within r, right? So this summand is positive. So I can drop those outside the radius of little r, but they are always inside radius capital R. So this is just log of the ratio of r and r times number of roots of g inside radius r. Right. So in other words, what I get is that suppose I want to control number of roots within a given circle, and I need two things. I need some handle on the behavior of the function on a bigger circle, number one. Number two, I need the behavior of this function somewhere inside the circle, not to be too small, right? And combining these two things tells me number of roots within R is upper bounded by the ratio of log and log r over r. So this is a very commonly used tool to count number of complex roots within a given domain. So let's use it for our purpose. So for our purpose, we're going to apply it, our function. Let's just call it P of theta is the convolution between phi and mu. Right? And then I can write it in this expectation form. Let's say phi of theta minus u, where u is distributed according to mu. And by assumption, u is at most a in magnitude, almost surely. So this is assumption. So the goal is to count number of real roots in total, right, in the entire real line of p prime theta. So this is the goal. And remember, I want to apply Jensen inequality. It only counts roots in a disk, right? So I need to first find a disk that encloses all the real roots. So this is step one. Step one is to localize roots, real roots. So what is p prime? P prime is the derivative of Gaussian density, right? I can differentiate inside this, and that's that. So I know that this is less than 0 if theta exceeds a, because u is between plus minus a, right? And this is positive. And it is also bigger than 0 if theta is less than minus a. So there is no roots, except the interval plus minus a. So this means all the roots is included in the interval plus minus a. And then I can apply and then that's basically it. So this suggests I should apply. So let's say this is plus minus a. So let me find a place where I have some understanding about this function from below, right? So in particular, let me choose this place, because remember the second ingredients about applying Jensen's formula, I need to have find a point where the function is not too close to 0. So indeed, let me evaluate on minus 2a. And again, this quantity is bigger than a, just by definition. So this is bigger than, a times at most exponentially quadratically small. So let me also apply, choose capital R and small r, which is 3a and 4a, right? So in this picture, what I get is that this is where the real roots is. So let me choose this circle to include everything. And let me choose a bigger circle. R. So this is the picture. So on the bigger circle, the maximum you can get is at most exponential again. And then combining these results will let me control, right? So the end result is log of 2 logs e to the ca square, ae minus ca square, and 4a and 3a. And this is big O of a square. So this allows me to count all the roots here, which allows me to count all the roots here. And that's all the real roots. So that's the proof. So, and clearly this is a matter of, there is a crucial result of localizing the roots. And this crucially relies on the fact that I can write it as expectation. If the weights are negative, then it's not true. I think I'll just end here.
Thank you very much.
Yeah, sorry about the promise to the radius torsion function. I didn't have time to get to it.
You'll come back we hope so.
Yeah.
Thank you.
Yeah.
Any questions?
Yeah. Yihong,
yeah, please.
very nice results. So is this connection with rate distortion in the archive paper?
It's not, but I can just state it right now. So it's about there's a paper by Rose, Kenneth Rose.
Yes.
Which is the parallel 90 something.
Right.
To the Smith paper that shows if you
Yeah.
have px, which is on plus minus a, then r of d, which is the inf over mutual information, subject to, let's say, quadratic distortion, is achieved at a py that is discrete.
Yes.
So you can show that
this has been used by Nobel Prize winning economist.
Oh yeah, I heard that.
Prices are sticky.
Yeah. Tension or something. Yeah, rational attention. Yeah.
Yes.
Or irrational, whatever that is. So we can prove the following two things. Let me just say the end result. The end result is, of course, the finitary version of this result says how many points does By have? And the results is the following: a square times the derivative of this here on this order. And some comment on the behavior here. I think if let's say the distribution has a density, then the rate distortion function grows logarithmically. So this derivative should be like 1 over d. And this is consistent with what quantization gives you. Essentially, we know for small d, quantization is the best you can do. So this tells you, roughly speaking, I mean, kind of it's it's consistent with this observation. So this is the reason this is possible is because first, let's write it in a penalized form. I'll write in this notation because it's closest to Gaussian. So remember, there's this translation of the minus derivative to the penalized and the constrained form. And this is exactly equal to the following. So there's some constant depending on sigma minus the maximum of the following function, which is again over all measures. And here, this is just over log of pi convolves phi evaluated at x. And x is the original x. And what the results about counting derivatives, critical points showed these argmax is pi star, which is exactly what y is. This is the same as py. Has at most a square over sigma square atoms. So it's the same lemma. And because here, what matters is the support of x. And before, we only use the support information. So this is what the connection to rate distortion function. And yeah, that's it.
So this is actually very interesting because this is kind of like, this has no data here. So this is just an optimization.
No, yeah,
problem.
Exactly, yes.
So here's the question then. You're familiar with the terminology reverse I projection, right?
Reverse I projection. So
okay,
DPQ
so
and DPP, one of them is the...
Yeah, so conventional I projection, you look for the minimum relative entropy when you fix the reference measure, and then the dominated measure belongs to a convex set.
Okay.
Okay. And of course, there are beautiful results about this.
That's the one that shows up in large deviation.
Sure.
Yeah.
So if you now swap the role of what you know, which in the previous case is the reference measure, now suppose that is the dominated measure. Okay, and then you are minimizing that over. You are minimizing over the reference measure that belongs to a convex set. Okay, so this is in fact, if you think of this dominated measure as the empirical measure, then this is the same thing as maximum likelihood estimation.
Yeah, that's right. Yeah.
Right. So now the question I have is that perhaps what you would be able to show is that there are some, let's call them empirical measures, that lead to this very sparse solution.
That's right.
And then you can prove another result that says, well, if this empirical measure comes, if this measure comes from being the empirical measure of an IID process, then it satisfies whatever condition that is.
Yeah, so here exactly that's what happened. So we used these results when X has the empirical distribution 1 over n delta xi's. And the only property we used is just its support, its range, the max and the min.
Oh, okay.
Yeah,
wow.
because
I see.
yeah, it's a very crude thing. We didn't even use the fact that they are generated by IID process. We just used if they're generated from process,
so
the maximum and the minimum cannot be too extreme.
So then
because
it's
if
very
you remember
robust.
the previous bad example where they actually have the solution is not sparse, right? It has a lot of atoms. Those are situations where the extremes are only order of n. But if they are IID, they are only order of root log n. And that's the reason, yeah.
So it's very robust against the independence assumption.
Yeah, so these deterministic results is the key, and this is the afterthought. So here it's, yeah, exactly. So if you only have some guarantees on the range, then you know what is the number of solutions.
Very nice, very nice. And then another thought, which is very nebulous, is that Kiefer-Wolfowitz, in a way, would remind one of CTW, context-free weighting.
Okay.
In the sense that there you say, okay, so Kiefer-Wolfowitz says, okay, so we have this nasty problem, so now I'm going to assume that we have a very general mixing, a very, very general mixture. And context-free weighting, in a way, is doing this also because it's essentially averaging over all possible context trees.
I see. Okay.
So the natural question to ask then is whether there is a parallel result there, where at the end of the day, the solution that is chosen by the CTW is like a sparse model. It's not. It's only a mixture of a few sources.
So I can tell you something also very nebulous, but along the line of universal compression that I've been thinking about. So exactly of this style. So if you think about what is the mutual capacity redundancy type of quantities that shows up there, you have theta and xn, right? So you can also ask the question, this p theta is the worst case prior. And what is the behavior of this thing? So is the solution sparse in the sense of, so I think it's easy to show it's at most n. I think this is just a Cartesian type of argument. If you have n, so you know what I mean, right? So px n is p, given theta is p theta to the n. Mm-hmm. But we know in redundancy, this quantity scale as 1/2 log n. So this constant is important. So you cannot expect for p theta to take less than polynomial number of values because it grows as some constant times log n. So maybe it takes root n values. So this is my feeling. It's just a hunch.
Okay.
Yeah. So I think the high level slogan here is to beat Carey theory, I think. Carey theory says n, there we show this log n or something else. Here I felt maybe it's root n. So yeah, but I'm not entirely sure about to more algorithmic things like CTW. It's a good question. Prakash, do you
Hi. I had a question also.
Yeah, please. Yeah.
You mentioned that is, if you do maximum likelihood estimation, you go into this reverse I projection.
Okay.
Where the first measure is the one is the empirical measure, and then the second measure with regard to you minimize is the one over the family of interest. But then if you restrict yourself to an exponential family, then things become considerably less complicated. And
yeah, more transparent, right? Yeah.
now, is there an analog of that kind here?
Yeah, I'm not sure, because first of all, this connection to maximum likelihood only makes sense if things are discrete, right?
Yeah, yeah.
I think that's it. Yeah. So for mixture of Gaussians here, it's hard to say. So the first results that I was ever proved along this line by CMAR would deal with Poisson mixtures. So those it's fine. So you can think about just integers. And that results, you can prove it. I mean, the counterpart for these results, you can prove it without any complex analysis. The reason is that this derivative, this magic function, is just a polynomial. Of what degree? Of the degree which is the largest of your x1 up to xn. I mean, you have n points drawn from some discrete distribution. A lot of them will be collisions.
Yep.
Right? The largest point you can get is something like log n.
I see.
That you can get it for free without complex analysis.
Yeah.
The complex analysis is just to deal with non-polynomials, I think. Yeah.
Sure.
Right. Yeah.
Well, thank you for a very nice talk.
Oh, thank you very much. Yeah.
At some point, come back again and maybe tell us a little more about connections to capacity.
Yeah, yeah, sure. Yeah. So this paper discussed the Smith problems. I think it's yeah, it's very nice.
Right.
Okay. All right. Thanks a lot.